So the next section, chapter 14.2, is called Evaluating Limits. Evaluating, since Algebra 1 just means plugging in values and see what we get out. So there's a three-step process when we are evaluating limits. The book does multiple steps and separates limits for addition and subtraction. You guys will see all of that next year. What it's important to know is to evaluate a limit. First, plug in the value c for whatever limit you have. So we have limits as x approaches some value c. Plug in value c and see if you get an answer. If you do, that's what the limit's going to be. We kind of showed that in the last section using our tables, but just to be clear, if you can plug in a value, if the value of x is in the domain, then it exists. The second step, if you can, simplify the expression algebraically and see if you can get an answer. So sometimes we get 0 over 0, but we can do some algebra and we can simplify, and then we can plug in a number and we can get the limit. The last case, sometimes you'll get 0 over 0 or infinity over infinity or negative infinity over negative infinity, and we call these the ambiguous cases, and we'll have to do more work with them further along in calculus. So if you do end up with that and you can't simplify anymore, we just write infinity or negative infinity for now. So trying out some of these example problems. Straightforward. The limit as x approaches 3 of 5. If you think about this graphically, this is just a horizontal line at 5. And so no matter what, if I plug in any number for x, the value I get out is 5. Same thing with the limit as x approaches 0 of negative 8. It's just negative 8. If I have a linear function, if I want to know the limit as x approaches 5 of negative 4x, this is just a line with a slope of negative 4. So just plug in 5. See if that comes out, and we get negative 20. Same thing for d. The limit as x approaches negative 2, we plug in negative 2 in for x. See what we get out. We get negative 6 minus 5, which is negative 11. So super straightforward. Last one, quadratic. See if you can plug in. So it's 5 times 2 squared, which is 20. So all of these polynomials, if you will, the limit exists. For example 2, just a couple more. Let's say we have 4x cubed, it's a polynomial. We could plug in 2. We have 4 times 2 cubed, so that is 8 times 4, which is 32. B, or just plugging in 1. So 3 times 1, which is 3. 3 minus 5 is negative 2. Negative 2 to the 4th is 16. How about here? If I plug in 0 for x, that goes away. I have the square root of 8, which if we wanted to simplify is 2 root 2. We should be able to do that pretty simply. And d, if I plug in 0, I get 0 minus 0 plus 3 to the 4/3. That's just a number. That's 3 to the 4/3. And if you guys remember how to do this, you take 3 to the 4th. This is the cube root of 3 to the 4th power, which, if we simplify that, I don't even have to work out what 3 to the 4th is. That's a 3 cubed root of 3. All right, last example. This one starts to look a little more complicated. First, we plug in a number, see if it exists. So we get 5 minus 1 plus 2 over 3 plus 4. So I have 4 plus 2, which is 6, over 7. We get a number. That's what my limit is. If I look at the graph or the table, all I'm doing is plugging in this value that I am approaching from the left and from the right. All right, so on the back side of these notes, problems get a little more interesting. So if you look at example 4, we're looking at the limit as x approaches 3 of this function. So just like we did before, plug in 3, see what we get. I get 9 minus 3 minus 6 over 9 minus 9, which is 0 over 0. If you get 0 over 0, we have to do some work. And usually that means we can simplify. So here, I'm going to write this next step. The limit as x approaches 3. Factor the top, which is x minus 3, x plus 2, over difference of squares, x plus 3, x minus 3. Now we see that these x minus 3's cancel out, and we're left with the limit as x approaches 3 of x plus 2 over x plus 3. Now, plug in 3 and see what we get. So this is 3 plus 2 over 3 plus 3. So a problem that went from 0 over 0 becomes 5/6. So even though this function is undefined at 3, we can simplify this algebraically. Simplifying algebraically means it has a hole, and that's what the value it's approaching. Same thing for b. b is a little more complicated because we have to actually know how to deal with fractions. So if I plug in 0, I get 0 minus sine of 0 is 0 over 0. So another 0 over 0 case. Here, the trick for this question is to split up the fraction to be 5x over x minus sine x. Which is the same thing as the limit as x approaches 0 of 5x over x minus the limit as x approaches 0 of sine x over x. Well, 5x over x, these x's cancel, so this is the limit as x approaches 0 of 5, which is just 5, minus, well, we did this problem on the table. If we look back on our notes from the first section, we know what the limit of sine x over x is. That's already come up, so that important reminder comes back, which is 1. So this is just 1. So this problem is just 5 minus 1, which is 4. Moving on. So example 5, we want to find the limit. If I plug in 2 here, I get 8 minus 4 plus 8 minus 8. Let's just double check. 8, 4 times 2, that's 8. Yep. Over, if I'm guessing, this is going to be 16 minus 16 plus 2 minus 2. So again, I get 0 over 0. So I have to do some simplification. If you remember back to algebra, we did something called factor by grouping. So what's common to x cubed and x squared? And then what's left is x minus 2. This is the top. What's common between 4x and 8 is 4. What's left is x minus 2. And I'm going to do the same thing on the bottom. X squared leaves you with x minus 2, 1 x minus 2. That's the tricky one. So that leaves us with our factors of, and this is all the limit as x approaches 2. It's important that we continue to write that. So the limit as x approaches 2 of x squared plus 4, x minus 2, over x squared plus 1, x minus 2. Now our x minus 2's cancel out. Now I can just see if I can plug this in. So 2 squared plus 4, which is 8, over 2 squared plus 1, 5. So just some simple algebra, and we can work these expressions out. We'll save example 6 for the last problem. So example 6, for average rate of change, if you remember, rate of change is the change in y over the change in x. So what we do here is we take the difference in the y values, so we do f of x minus f of 2 over x minus 2. So this is how we find average rate of change. And this question is asking you, what is the limit as x approaches 2 of f of x minus f of 2 over x minus 2? Well, if I plug in what f of x is, that's just x squared plus 3x. And if I plug in what 2 is, I have 2 squared, so 4, plus 3 times 2, which is 6, over, so that's minus, and this is x minus 2. Okay, now we go, can we simplify this at all? Or can we just plug, what is the limit as I plug this in? So looking at this, 4 plus 6 is 10, so this should be minus 10. So that's a little fix. Now, if I plugged in 2 to this function, I get 4 plus 6 minus 10 over 2 minus 2. So that's our 0 over 0 case. So we should be able to simplify this. And mind you, that's the limit as x approaches 2. Okay. So we can factor this. Numbers that multiply to negative 10 that add to positive 3. So this is the limit as x approaches 2 of x plus 5, x minus 2. And look, our x minus 2's cancel. So now I'm just asked for what's the limit as x approaches 2 of x plus 5, which is 7. So if we look at this, the average rate of change of a function, so not just a line, but of a function, we can get out a number. And that's this idea right here, the average rate of change, is a big part of calculus. So we'll spend a little bit of time on this in class, and you're going to spend a lot of the time in calculus next year on this. All right.